I'm going to be talking about the new leap in mobile hardware and software. We have a new generation of hardware and rendering techniques that we can do starting from this year. So a little bit about me. Please call me Smedis. That's what I'm used to since many years in the game industry. And originally I'm from Sweden, but live in the US now with Epic Games. But I came from the European demo scene. That's how I grew up, kind of. All right, so we have the next-gen hardware and next-gen rendering techniques. This year, this transition into the next generation stuff has made us shift our goal at Epic Games. Previously, we were fighting and driving very hard to get AAA console graphics and working on a mobile device. But we've done that, we've passed it. Now we're shifting our goal to making AAA PC graphics run on a mobile device. That's kind of where we are now. So the new generation I'm talking about is the GPUs are becoming full-featured, basically having all the PC and console features on a mobile device. It's like the shift from DirectX 9 to DirectX 11. On the OpenGL side, it's called ES 3.1. And AEP, that stands for Android Extension Pack. That's what Google announced with their Android L, which got a name that I forget what it is. Lollipop? Lollipop, yeah. And what I meant that the console graphics was done is that the peak performance on modern GPUs on mobile is kind of on par with what the Xbox 360 and the PlayStation 3 did. About 300 gigaflops and 26 gigabyte per second bandwidth. So that means that we're past the consoles generation. We're now shifting into our new PC goal. Here's a little graph that I made to show kind of the generation leap. Here in 2014, this is where we were meddling for several years. This is kind of what the best of the GPUs could do back in those days. But we're way past that now. You can see the kind of GPUs that I talk about for the 300 plus gigaflop. That's the Qualcomm Adreno, the Nvidia K1, and Imagetech GX6650. That's the kind of GPUs that are coming out or already out this year. Also, it's important to note that this is for FP16 performance, not FP32. That's a very important point that I'm going to come to later in the talk. The other thing that has happened this year is things like new APIs, like iOS 8 Metal API. When Apple announced that at their WWDC, which they sometimes pronounce WWDC, it's an Apple thing. We did a little demo on stage and showed off Metal. And we found that, or I measured the same rendering on OpenGL, and I measured it on Metal. And Metal was 20 times faster on the CPU. So it is a CPU thing, much more efficient on the CPU. Basically, so OpenGL used 30% of the render thread of the CPU. It's a lot of overhead for an API, right? It's hard to make any number of draw calls if the system just takes the CPU from you. But with Metal, it goes down to 1.6%, basically nothing. So the CPU is completely in your control. So you don't have anyone else to blame for your performance. This is the, yeah, the gamma is a little bit wrong on this display. But that's the demo that we did for the Metal. Okay, on on the GPUs, mobile GPUs, so while I say it's, the performance is like the Xbox 360, and we're trying to do PC graphics now, they are fundamentally different than PC GPUs or console GPUs in that they're mostly tile-based. This is extremely important to know exactly what is going on. It's the, if you do it wrong, you can basically cripple your frame rate. If you do it right, you can get excellent results. There are some mobile GPUs that are direct rendering, but the big market share is on the tile-based GPUs. So, tile-based GPUs, what does that mean? It means that the screen is split up into tiles. Each tile fits on the GPU. There's no render target that is in RAM. This is actually on the GPU. So each pixel is basically a register, hardware register on the GPU. It means it's very fast to render to. Do alpha blending is on the GPU, very power efficient. However, it has some properties that you need to think about. So when a GPU processes the frame, it does it only for one tile at a time. It processes all the draw calls for one tile in every draw call in your frame. And when it's finally done, it exports that tile memory to RAM. And then it starts the next tile. So this is a little bit of a schematic of how it works on Imagetech GPUs. Imagetech, Imagination Technologies. If you look on Google and Wikipedia, it would say that that's the GPU that is in iPhones, all iOS devices, and some of the Android devices. So it's an important part, GPU family to consider. So the stuff that is in orange here, those boxes are on the GPU. The green is RAM, and that part is the game. It's not scaled, to importance to you maybe. However, this dashed rectangle here, that's what repeats per tile. So you can see that the vertex processing happens only one time for the entire frame. So it does the vertex shader for all the draw calls, saves that out to RAM. So basically, all your interpolator data, it doesn't start to rasterize like on a normal GPU. It saves all the data out to RAM. And then the pixel processing starts kicking in, one tile at a time. It basically reads from RAM the vertex shader output for the tile. It's been sorted and prepackaged nicely, all handled by the hardware. Imagetech has a secret sauce here, which is very convenient for us programmers. There's a nice GPU to work on the first time to get up and running. Because it has hidden surface removal, it means that any overlapping pixels, this is per pixel, not just per triangle or anything, you won't rasterize or process any overdraw, any pixels that are in the background. Only the frontmost pixel will actually have the pixel shader run for it. It's a step better than Z buffering, Z call. And then it writes out to the tile memory, which is basically demade out to RAM. This is how one of those new next generation GPUs looks like internally. This is something that wasn't actually announced publicly, really, but this part is completely new. Besides that, it's basically a DirectX 11 part with full features, a real next generation GPU. It has this extra special hardware for 16-bit floating point. This particular GPU, which may be in some popular devices today, it does a different instruction. It doesn't do a MAD like normal processors. They can do MAD. That's an if. That's pretty much the two instructions they can do. But the FP16 has a SOP, which stands for sum of products. Which basically, if you remember register combiners back in the days for Nvidia, that's the instruction they had. The newer GPUs are coming out after this. The next version of it, actually it does a normal MAD, but this one was a little bit special. That means that it does more operations per clock cycle, and that's why it's faster than FP32. So this is how much faster it is with FP16. On that existing GPU, it's 50% faster because of the SOP instruction. The new XT versions that are coming out now, they instead go over to regular MAD instructions, which is a little bit easier for the shader compiler to actually generate MAD instructions. So you can actually use the FP16 path more often. And this is automatic in the shader compiler. So it has double of the MADs instead. And on Qualcomm, it's always 100% faster, and it's been that way for a long time. FP16 is kind of, that's what you need for HDR lighting and linear colors. You don't really need FP32. So on mobile, it's important to specify medium P as your precision, so you can use FP16 and do that as much as possible. All right, so I talked a little bit about the hidden surface removal. So it's only for opaque triangles. So it won't be for the alpha blended particles or windows and that kind of stuff. But it's also important to know that alpha test or any shader that uses discard, even if it's opaque, like you could think it is opaque, the GPU doesn't see that as an opaque triangle. So any masking, that will not go through the fast hidden surface removal part. And since it has that removal, that means that you don't have to, and it does all the sorting on its own, so you don't actually have to sort your draw calls front to back or anything. That means that you can instead sort on state to minimize state changes. So it's very, very convenient. And it's only Imagetech who has this feature. All right, so the problem with tile-based GPUs is the resolve and the restore of the frame buffer. That can be add a lot of latency to your rendering if you basically don't switch render target. Anytime you switch a render target, then the GPU will have to flush all the tiles, finish rendering all the tiles, write that out to memory. And if you, in the very next draw call, you switch to render target, and the next draw call is reading from the result, basically the GPU will have to wait until all the tiles have been processed and written out before it can start the next tile with a new render target. There are some various GPUs have various overhead on this, but it's always a big hit. It's a kind of performance hit that can half or even worse drop your frame rate. So the fastest case is to have a single render target for the entire frame. No post-processing passes, and no render target switches. That's the absolutely fastest you can go. However, to get some nice graphics out of it, actually you have to do some render target switches. But just know that you have to be careful when you do those switches and measure before and after, anytime you add a new pass. Also, the Nvidia Tegra GPU, that was in the kind of family, GPU families that were direct rendering and not using tile-based. So that meant that we were working on our rivalry tech demo, showing off all the new next generation graphics. It was easy for us to use the Tegra GPU as a first bring up GPU for this technology. I'm going to show you the rivalry demo at the end. All right, so what can you do to minimize the impact of a resolve and restore? There's two things. This is for avoiding loading an FBO from RAM into the tile. This is a restore optimization. So anytime you switch a new render target, you have to tell the driver that this new tile, the new render target that we're going to render to, we're not going to continue to render from something that we rendered previously. We're going to start all fresh. Please don't load anything from RAM. And you can do that by issuing a clear operation that tells the driver, okay, they're going to start fresh. The clear, since the tile memory is just registers, clear is pretty much instant and extremely quick. It basically just sets a bit pattern that it's cleared. And when you clear, you have to clear everything. All color attachments, the depth buffer, stencil, anything you have in the FBO has to be cleared. And then, of course, if you're running on a direct rendering GPU, like the Nvidia Tegra, then you should not clear, because that actually does take time. Because then you actually have to go and fill in memory in RAM and use up memory bandwidth. So you really have to basically do a couple of ifs to see what GPU you're running on and what kind of GPU you're running on. The other way is for resolving optimization is you can use a GL discard frame buffer extension to tell the GPU or the driver that, hey, I rendered a depth buffer here, but I'm actually not going to need it for any future draw calls, so you don't have to save that outer memory. Only the color is important. And then, as always, you have to profile for performance. This is an excellent profiler tool in Xcode for iOS devices. It's called GL Debugger. And this is a frame capture from the Soul demo that we did for GDC this year. These are all the draw calls we had, and I selected a draw call that is part of the anti-aliasing. You can see how the performance of that draw call. This is taking 1.73 milliseconds on the pixel shader for that one draw call. It's a full screen draw call, so it touches a lot of pixels, so it will be heavy on the pixel shader. On the right side there, you can see the actual shader. And kind of nice is that this tool supports edit and continue, so you can change the shader, see what new performance you get on the draw call, and iterate pretty quickly. Another thing that is kind of unique to GPUs on the mobile devices, at least those that are tile-based, since the tile memory is on the GPU, it's just a register, means that you can just read it too, if you want to. So there's an extension called frame buffer fetch, which gives you a new variable, which is basically that tile memory, the register for your current pixel. Normally, on a desktop GPU, you would have to go to RAM to try to get that, and it gets all messy. The other extension is shader pixel local storage, which is a joint extension between Imagetech and ARM. It's coming out now. Not sure if it's in an actual device right now yet, but it's coming. So one thing you can do with this is to avoid switching render target. You want to stay in the tile memory. So you can do some full-screen post-process quads. For example, tone mapping, where you only need to read from the current pixel. You can read the background color, do your tone mapping, and write out the result. And this is basically a post-process, but you don't have to do any render target switches or go out to RAM in between. Yeah, please. So here we have an example of the programmable bending that we did in the Sol demo. Again, the gamma is kind of wrong here, but you can see on the brighter part, the water, those are softly blending with the background. So any translucent particle that would intersect the background geometry, normally you would get a straight line, a clip line, which is pretty nasty. You can see that in a lot of games on particles. Smoke, for example, that cuts through geometry. Nasty, nasty lines. On an Imagetech GPU, we can use a frame buffer fetch and read the background depth value, which we have stored in the alpha channel. And then we know our current depth, so we can blend out as the particle comes closer and closer to the background, we start to fade it out. So there is no intersection line. And it's cheap to do. You need to use some force, brute force. Okay, the other thing we do in Unreal Engine 4 is to optimize how we sort our draw calls. As I said, this is a little bit differently depending on which GPU we're currently running on. For all platforms, even desktop, mobile, console, whatever, we group our draw calls by shader. This is to minimize state changes. And on an Imagetech GPU, that's where we would stop. That's all we need, because it has hidden surface removal. We don't have to optimize for overdraw. On other GPUs, for example, a Qualcomm GPU, which is tile-based but still needs the extra sorting, you can see some numbers that we had, the kind of savings we got on a Qualcomm GPU for the different kind of sorting we did. There's a specific mention for the skybox. The skybox should always be the last draw call you do. It should never be the first, which happens sometimes for some reason. Because the skybox is often occluded by all the graphics you have on top, right? So while it covers the entire screen, only a few pixels actually are visible often, or even if you go indoors and you're still rendering the skybox. It should be last so it can be properly Z-called. But again, on an Imagetech GPU, it doesn't matter which order it is because it will only process the topmost pixel anyway. The other big optimization you should do is don't render to native resolution. Render to a resolution that matches your performance target. Because here's an example. On an iPhone 5S and an iPad Air, they have the exact same GPU, same performance on the shader unit, same memory bandwidth, everything. However, they have vastly different screen resolutions. That means that the iPad Air has to run the pixel shader on 4 times as many pixels if you render native. So don't be sloppy. Set a resolution that matches the common performance target that you just decide. So on an iPhone 5S, we'd run at native 640p. On iPad Air, we would run at half resolution. And then we have about the same kind of pixels that we have to shade. And that means that we don't have to cut any features or anything. It's exactly the same feature set, just at a matching resolution. One big target and deciding factor in Unreal Engine 4 for bringing PC graphics to mobile is to have the same content. In UE4, we decided to stick with HDR colors, high dynamic range, linear color space on both PC and on mobile. Because if you are rendering in gamma space, it's very difficult to use those textures and these assets on a HDR platform. So if you want to have, you basically have to pick either HDR and all your assets are in HDR format, or LDR, or gamma space. It's very difficult to have a game using the same textures and the same assets, the same particle effects run on HDR on PC and gamma space on mobile. So as an example, here's a screenshot on how it looks on PC, and here is a screenshot on mobile. So while there are some differences, the lighting is a little bit different because we have made some different choices. It's pretty much a similar experience you get. The way we're authoring content to be the same but still have some optimizations per device. In our material editor, the artist can, it's hard to see on this display, but some of these branches in material may execute only on certain devices. So it's basically, as we add feature levels, what we call feature levels, more and more of the material gets enabled. But it's just a single material that runs on all platforms. For our static lighting, we have directional light sources. This is on both PC and mobile, with sign distance field shadows. The sign distance field shadows is an important part because it allows the edges of the shadows to be completely smooth, instead of if the shadow texture had an actual shadow color, then you would see some pixelation and jaggies from the texture lookup. But because it's in sign distance field, it's interpolated, so you get nice, smooth transitions. So what we did for mobile, you can see how the light maps and the shadow maps are constructed. We have a couple of different textures. So we have some special considerations on mobile. In particular, the PVRTC, which is what Imagetech has for texture compression. That texture format doesn't have an uncorrelated alpha component. So it basically doesn't have something that corresponds to DXT5. So on mobile, we did this for all mobile because of this. We decided to, instead of having an alpha channel that would contain the log luma in an uncorrelated alpha channel, we made the RGB values and the log luma correlate by putting them completely pre-multiplied into the RGB and have no alpha. So instead, to split those values up again in the pixel shader, we have to derive the log luma again with ALU instructions and some extra math. But it made it work. Then another important part is for HDR and physically based shading is image-based lighting. So this screenshot, none of the pixels here on this screenshot actually receives any direct sunlight. This is all in shadow. So all the lighting is coming from cube maps instead, with reflection information. On PC, those cube maps, we can have multiple of them. On mobile, we decided to have just a single cube map. So the encoding is a little bit different. We have RGBM encoding on mobile, where it's just straight FP16 on PC. But so there's some limitations to it, but it kind of have the same feeling in the result on the screen. In total, this is a kind of post-processing. This is basically the rendering pipeline for the all post-process on mobile in UE4. You can see an important part here is to minimize render target switches, right? That's the key limiter on mobile. And you can see all the arrows. Each one one render target can be reused for different passes. Try to reuse as much as possible. Also, most of these use very low resolution render targets. You can see go all the way down to a 32th of the normal resolution, or 64. So even though they do write out to memory, it's not a big hit anyway because they're small, except for a few passes at the end there that is completely full resolution. So on the mobile depth of field, we have again, it's slightly different from PC, but similar enough to bring that AAA PC mobile depth of field to mobile. On mobile, we decided to, instead of making it very, very blurry, we limited it to just a little bit of blur, just to get a nice feeling, and have the transition between the near crisp plane to the far plane to the blurry distance, have that transition as smooth as possible. So we did some optimizations and choices on mobile that made it much faster, but there is a slight difference compared to the PC version. So one thing we did, and this is in particular to save render target switches, in the alpha channel of the frame buffer, where we normally store the depth, we noticed that we could combine two separate values and store in a single alpha channel. We had the depth value, which is where the depth of field could be in focus or have a transition. That is encoded in the 0 to 1 range. And then we have the sun intensity for bloom, which is in our case, it's the sun is always very far away. So basically, we put it at the 1 depth at the far plane, and everything above 1 is the sun intensity. So we can combine two values into one this way and save an extra render target. Here's another thing we do on mobile is to combine many passes into a single Uber shader. On a PC, it's not such a big deal to have another quad on top of another quad. But on mobile, those render target switches are extremely hurtful, especially if they have to run in full resolution. So we have Vignette, Bloom, and light shafts in the same shader. This is an example of how it looks on a mobile device. While they are applied in one single pass, they are composited at a smaller resolution. All those intermediate passes you saw in the graph before, those are usually, we try to keep those at low resolution. And then for the Uber shader, we have source data in a single render target. So we can apply it with just one texture fetch in the tone map pass. The light shafts on mobile is also a little bit different than PC, while similar enough. They are monochromatic, so it's just a single color. You noticed that it was a little blue tint on the light shafts in the screenshot earlier. Whereas before, we would actually read the background pixel and pick up the color from the background. That requires another render target switch, so we optimize that out. On the bloom, we worked hard to try to get a big, blurry bloom kernel that we had on PC, and we were able to do that on mobile too by doing a lot of downsampling, so we can cover many, many pixels. On the downsampling, we do one downsample at a time in many phases. And each downsample, we're doing a lot of texture fetches. You can see we're actually doing 15 texture fetches during the downsampling phases in that kind of pattern, circular pattern, whereas we do 7 taps when we go to upsampling again, back to full screen. Those upsampling, they combine 2 different resolutions to generate a higher resolution. Another thing we've been pretty proud of to get onto mobile is our film post tone mapping. And with film, it means that we're trying to recreate what actual film, on photo film would do, rather than being cinematic. So these are 2 screenshots with different settings. This is a graph of the passes and the different features that we combine in one single Uber shader for the tone mapper. So the tone mapper does a lot of things. You can notice, oh, the tone mapper does bloom, vignette, and light shafts. And it does a lot of other stuff. The only actual tone mapping part of it is in the right corner, that little box. So it's a lot of features we crammed into a single Uber shader. The last part is anti-aliasing. This is a little bit interesting because the GPU has MSAA as a hardware feature. And that is really good to use, actually, on tile-based GPUs. However, you only get edge anti-aliasing with that. And in our HDR world, we can get a lot of aliasing from within a triangle because of a normal map that is with specular highlights. You can flicker a lot even within. So therefore, we have our own shader to do anti-aliasing as a post-process. It's a little bit special in that it takes 2 frames. We save the frame of the screen for the previous frame, and we have the current frame, and we kind of blend those together per pixel, depending on how much it changed. So 1 frame, the screen is kind of moved up a little bit, and then the next frame is moved a little sideways, and go back and forth like this, and then blend it together to make it smooth. So it says here we're currently not using the hardware MSAA, though that's not quite true because we did use it for the metal demo, and we have that option now in the engine. So this is kind of what it could look like. Black, very dark, moody. Well, that's a Soul demo. Okay, so for the final slide, I would like to talk a little bit about the Android extension pack, which is the next generation of rendering APIs for Android. One big part is that it has a bunch of extensions, OpenGL extensions, that are required, that every vendor has to support to be able to get the approval AEP stamp. So an example of a GPU that supports all of this is the Nvidia K1. And I'm going to show a video of the K1 running a rivalry demo. So that started out as a high-end PC demo. The characters, they come from another high-end demo that we were showing at GDC a little while ago. And now it was running on a mobile device. And to show that it was not just a video, it's actually running on this device. If I hit OK. This is in real time on a mobile device. This is the Nvidia Shield tablet that you can actually buy. And it runs at about 30 frames per second at 720p, I believe. So not at native resolution. But it's all the PC graphics, pretty much everything that we have on PC running on the mobile. Oh, actually, I turned that off before. After the cinematic part, it comes to an interactive part where you can actually move around. I could put that back again, so if you want to check it out after the presentation. And that's it. And oh, by the way, so besides that Unreal Engine is like, it costs money, $19, but you know, all the examples and all the source code, you can actually read everything. And you don't have to subscribe. You can just pay the $19 one time and then cancel. You still have all the source. And you can play around with it as much as you want. Thank you.
All right, thank you very much. So, are there any questions? There you go.
You mentioned using Uber shader. Isn't there a limit on how much instruction you can use within a shader? And did you hit the limit on how to make any compromise on this? Or is it just okay, the limit on 3.1 is way beyond what you need?
The limit of what?
Of GPU instruction in the fragment shader.
Each GPU instruction in the...
In the fragment shader?
Oh, so how many, the sizes of the, so it's actually, this is true for all platforms pretty much, but especially on mobile, on these high-end GPUs, you want to actually have very long shaders. You need to have lots of instructions because, for example, on the Qualcomm Adreno GPU, the SIMD is extremely wide. It's not like just doing a VEC4 in parallel. It's doing lots of data points, lots of pixels in one instruction. And you need a lot of ALU instructions to cover any texture fetches, for example. And the bandwidth, though the bandwidth is great nowadays, is reaching up to like the console kind of bandwidth. It's still a far cry from, for example, 256 gigabyte per second memory bandwidth that you can get on a dedicated desktop GPU. So you need to have a lot of instructions in your pixel shaders to cover any texture fetch.
Yes, you need to have a lot of instruction, but there's also a limit on a maximum instruction beyond which the shader compiler will complain, I guess, at least on PC.
Yeah, though the limit is with OpenGL 3.1, you will hit performance issues way before you hit the limit. Except there are some bugs in certain shader compilers that we are hitting, and it's not just that the shader compiler complains; it crashes if you long enough. That happened on Imagetech GPU.
And how does nowadays smartphones compares to, say, PS Vita? Did you have any check?
So the PS Vita is a previous generation. It's not the next generation GPU. However, it is an Imagetech GPU, yes. And it has things like frame buffer fetch and...
is it tile-based also?
Yeah, it is tile-based. And with frame buffer fetch, you can try to avoid the render target switches, you can do basically post-process passes while still being on the GPU. So it is quite a cool device. I like it. But it is a previous gen, so it doesn't have like compute shaders and that kind of stuff.
Yes.
Oh, by the way, about shader instructions, we normally use about, it varies a lot from draw call to draw call, but we use in the range of 100 to 300 instructions or so. And that's both on all platforms, kind of.
Anybody else has a question? I actually have one. Does the fact that, at least on iPad, you can stream your gameplay to an Apple TV, to a TV, I think you can do the same with, oh yeah, that is interactive, on Android. Does that affect the rendering in any significant way?
In an extremely significant way. The newer iOS devices, they removed some hardware that they had in older iOS devices to encode video streaming in hardware. So they're doing that on the CPU now. So that means that anytime you use just connecting an iPad to a HDMI or any external screen reduces the CPU performance drastically, which is, of course, a big problem for us if we're going to do a demo on stage where we're showing on a big projector, for example. It runs perfectly fine on device, on its own. As soon as you use an external display, yeah. So streaming to bigger displays has a CPU impact that is noticeable.
Okay, that's interesting and annoying because it always seems like an interesting use case for mobile games. So yeah.
By the way, on streaming, I would say that there's a standard called Miracast that is for streaming video. It is being built into TVs nowadays, and a lot of devices. It's an open standard. It's free to use. So it's probably going to be a big video streaming standard. However, it's not so good for gaming because it has some latency. So on that end, Nvidia has built into their GPUs, both on the Tegra and their desktop GPUs, their own thing built on top of Miracast that actually lets you play with good interactive latency. But that would be NVIDIA only. So I would hope that the industry comes up with a new, better standard for gaming purposes.
Okay, thank you.
About Metal, I believe they use a different shader language. Did you re-author your shader for Metal, for your demo, or did you cross-compile your existing shaders? And if yes, has it been difficult to implement?
We do cross-compile here. So it took some effort to, we have a cross-compiler that take basically HLSL code. That's what we start with, and then for different platforms, we compile it into their native language, so GLSL or Metal, for example. So that's automatic. There was a time when it was very difficult to do, but Metal changed to make it easier to do this cross-compiling. So nowadays, it's not too bad.
Okay, thank you very much.
Yeah, you can look at Metal. There's an optional thing for shader source that makes it may do a little bit of extra compiling on device, because the big thing was it was offline compiled, right? So it basically becomes console-like programming experience. But it made it a little bit tricky to do a cross-compiling for one feature. It's still in Metal, but it's optional to disable, and then it has to do a little bit of a shader patch at runtime, but we chose that.
All right, well, thank you very much.